Today, instead of an integral, we have a limit problem. It's the limit as n goes to infinity of 1 on n times the sum of minus 1 to the k plus 1 times the floor of n on k. Wow, okay, so we have a floor function here. Well, first I should explain what the floor function is briefly. The floor function of x is just the greatest integer less than or equal to x. So for example, the floor function of 1.618 would be 1. The floor function of 0.915 would be 0. The floor function of this negative number would actually be minus 125 because that's the greatest integer less than or equal to it. Now, when you have a floor function in a limit, you kind of might want to try squeeze theorem, and squeeze theorem is done by setting up an inequality for the thing you're trying to find the limit of. The floor function of x is obviously less than or equal to x, and it's also greater than or equal to x minus 1. So let's apply this to n over k, and ideally we want to find a inequality for the entire expression in the limit. How do we complete this? We only have the floor of n on k at the moment. Okay, well, we could multiply by 1 on n, which is clearly positive, and that would give something like this. Okay, now we have to deal with the minus 1 to the k plus 1, which is a bit annoying because that's negative sometimes, and when you have inequalities and a negative sign, you need to switch the sign of the inequality. How should we deal with this? Okay, well, we can just take cases for k even and k odd. So if k is even, obviously, minus 1 to the k plus 1 would be minus 1, right? Okay, so we just need to multiply that, but switch the signs of the inequalities as well and negate everything. Okay, so that would be something like this, and then we need to do the left one as well and put some negative signs. Okay. Yeah, I guess that works. Now we need to do the same thing but for odd. Okay, so suppose k is odd. Okay, so k is odd. Now this is easier because minus 1 to the k plus 1 would just be 1. So we're just multiplying by 1, which doesn't really do anything. Great, so now we want to sum this whole thing over k. So I guess we sum over k even, right? Because this is only for k even. So all the even numbers up to infinity starting from, I guess, 2. Great, now we do the same thing for odd, and we want to get the full sum, remember? So I guess we just want to add these together. You want to add all the even, add the even sum and add the odd sum, if you get what I mean. So maybe we write this as minus 1 to the k plus 1, and this is minus 1 to the k plus 1. Okay, but to add these two inequalities, we need to make sure they're in the same order, right? So that's what we do. Basically, I just switched the order of this even inequality. Yeah, okay. Now we have these two expressions. If we add these inequalities together, which is perfectly valid, we get this monstrosity. But this middle part is just going to be the full sum, right? Yeah, because the general term is the same, but we're summing over odd and even, it will just become the full sum. Great, so now we have an inequality for the thing we're trying to find the limit of. We just need to take the limit as n goes to infinity, right? Now we actually take the limit. Okay, so as n goes to infinity, okay, let me just write these in. So there's an 1 on n here. As n goes to infinity, this 1 on n would just drop out to 0, right? Yeah, okay, so we don't actually need to worry about that. We can just delete it. And the rest of it will just be a constant. So we don't actually need the limit. I'll remove it later. But the same idea is on the right side. We have 1 on n. As n goes to infinity, that goes to 0. Okay, so let's write these as minus 1 to the k plus 1. For k odd, remember, that's just 1. For k even, that's minus 1. Anyway, so now we can combine these two into one summation. We can do a similar thing on this side. It'll just be the same sum, actually. Okay, good. Now, because these sums are constants with respect to n, we don't need the limit anymore. Now we just need to find this sum, or more specifically, quote this sum. So if you write out the terms, it looks something like this. This is pretty cool. This is the alternating harmonic series, which of course converges to log 2. And the right hand side is the exact same, so we have our squeeze theorem. So by the squeeze theorem, this limit is just going to be what? Log 2. Wow, that's crazy. Where did the natural log come from? If you look at this, it doesn't look like it's going to have a natural log. Anyway, thanks for watching. I'll see you next time.